Okay, slightly sparse today. People don't want to hear about reproducible research. That's too bad. Okay, so this lecture is a brand new lecture for this term. I've given some talks elsewhere on campus about reproducible research, and I figured I'd finally roll this stuff in this class because I think it's important enough. And the neat thing about most reproducible research stuff is you actually have already learned everything you need to know to do reproducible research for the most part. So today I actually won't cover too much code until we get to sort of the last third of it, where I'm going to go through sort of an advanced data manipulation example. But that doesn't deal with reproducible research directly. Today I'm mostly going to be honestly ranting about things that upset me, which is non-reproducible research, poor organization, bad practices, that sort of thing. So, yeah. Today, I'm going to start by giving an outline of what reproducible research is, why it's important. Then I'm going to talk about best practices. And when I say best practices, I mean basically they're best practices for how you organize your projects, how you write your codes, or general approaches to it to make your life easier and your work more easily consumed by other people. And those things I'm going to talk about are mainly organization, portability, and version control. Then I've got a little kind of tangent on advanced data manipulation where I give an example of a real data manipulation problem that I had about a year and a half ago, and I'm going to show you the way that I solved it because it was fairly complicated. Okay, so reproducible research. Why do we want reproducible research? What is it? So first thing is that reproducible research is not replication. We hear about having a replication crisis in science and things like that. Replication is running a new study to see whether the results of a prior study hold. Usually replication is done in a different area, modifying the type of treatment somehow, using different subjects, something like that. That is replication. It is a new study on the exact same topic, but it is a new study. Reproducibility is about rerunning the same study that you did and always getting the same results, or allowing somebody else to take your materials, rerun your research, and have them get the same results, ideally with little or no effort. Okay? So, reproducible studies can still be wrong, and one of the fun things about reproducible research is that making your research reproducible actually makes it much easier for people to discover that your research is wrong, right? If everybody else can grab your research, download it, and immediately run everything you did and look at all of your code, if you made mistakes in it, it's going to be a lot easier for them to find those mistakes than if you did not give them your data and your code and all of those things, right? Reproducibility is about making your research practices transparent. You're communicating everything you've done to other people, or as much as possible. You're throwing it out there and being like, I welcome everyone to look at everything I've done in this project and judge it by the merit of my actual code. Reproducibility also means making minimal barriers to verifying your results. When I say minimal barriers, I mean somebody ideally should be able to download your research, maybe as a single zip file, unzip it to their computer, open that RMD file and immediately knit it, and it will just work and output the document. And they can go through all the code, see all the decisions you've made, but it just runs on the first press of the button. Very often when I receive homework assignments from people in this class, I cannot, even with that self-contained RMD, just run your results. I have to modify your RMD files because you do things like set a working directory or something like that that I don't like and I'm going to complain about a lot today. So we're going to get into that. But basically, minimal barriers and transparency. The thing about reproducible research is that any study that is not reproducible can be trusted only on faith, right? If you cannot get somebody's research and you cannot reproduce it, all you can really do is take them at their word that their stuff is accurate. Maybe you can read the paper and try and remake it yourself and reproduce it. Very often you might find you're totally unable to because you don't have enough information. Non-reproducible research should not be trusted. I don't believe in trusting people just on the name that they are. I know some very famous people and some people who are great in social science. I do not necessarily trust their research simply because they are who they are. And if I don't trust them, I sure as hell don't trust people I do not know. If your research is not reproducible, you're asking everyone else to trust you did everything right and came to those results. If people come to astonishing results in the research, you're like, oh wow, that is a really interesting result, and they don't share their code, they don't share their data and everything like that, 95% of the time I'd be like, wow, that's fascinating. I bet they're full of shit, right? I don't believe it for a minute unless I can sign their stuff. There's sometimes excuses to make your research non-reproducible, but they are relatively rare, much rarer than most people think. And I'm going to talk about some of those as we go through. Okay. So, there's different definitions of reproducibility, so we have different realms of reproducibility. Stodden kind of identified 3 different realms. There's empirical reproducibility. This is repeatability in your actual data collection. This is saying that somebody could collect the data, obtain the data for the study using the exact same method as you and get the same data that you have. Sometimes this is really easy if your data collection is coming from some established secondary source. It's like if they download the census data, they get the same census data that you do. Sometimes with field experiments, that would be a little bit more complex. That would actually be rerunning it to do it, but that's saying if they reran it with the exact same people in the same location at the same time, they would get the same thing. Sometimes that's something ambiguous and hard to prove, but if you document it well, then other people can at least replicate it later. We could say it's somewhat reproducible. There is statistical reproducibility. This is verification with alternate modes of inference. You're still looking at the same topic and using the same data, but maybe if you modify the methods to maybe reduce bias of some kind, do some trade-offs, you'll get fundamentally the same result. Sometimes people have do some sort of research project. They'll use mostly good methods, but they're not the perfect methods for it. Maybe you could adapt them slightly to get less biased statistical results. If it's statistically reproducible, it means they could take the data that they have, rerun it with the appropriate statistical method, and probably come to the same result. Sometimes you'll have people reanalyze research that's been done in the past. They're doing the exact same study. They're looking at the same outcome, using the same data and everything, but some new statistical method has come out and they can part out bias better, and sometimes they come to different results. This might be, you might say, is an inability to reproduce that research, or an inability to replicate it. It's kind of a fuzzy range depending on how much of a new study you consider it to be. Lastly, there is computational reproducibility. This is the reproducibility in cleaning, organizing, and presenting your data and your results. It's not the choice of the statistical model or the choice of how you collect the data or something like that, but this is just, we have our data, we modify it in some way, we run some analyses on it, we produce some results, and we interpret those results. This is the actual mechanical procedure of running the code on your data to produce your models, your output, everything like that. Computational reproducibility is something that R is really well suited to doing. We can have a workflow or a whole, like, I'll show later, path diagrams of software development in a bit, which is something else. But there's a way to, in R, very simply, to basically do your entire study in one button press, say inside of an RMD or inside of a whole bunch of linked files together. Python is similarly well suited to doing this. Basically, any programming language that does good general purpose scripting can do it, but the tools in R and the tools in Python are the best out there for doing this sort of thing. Computational reproducibility, no matter how well you do it, will not fix your terrible research design if your research design is terrible, and it will not offer any remedy for improper use of statistical procedures. Right? There is a reason that we learn research design and a reason we learn the statistics. You have to have some kind of knowledge to do those things appropriately, and your computer cannot automatically tell you how best to set up a research project or what statistical methods are best to use in your data. Those things are theoretical issues that you have to know something about to deal with. Your computer, however, can do a lot of help in making you clean your data, organize it, and present it in an appropriate fashion, and make it so that other people can do it with a single button press. Okay, so computational reproducibility has a bunch of different elements, which I'm going to talk about some of them today. The first is shared data. For somebody to reproduce your study, they need to have your original data or a reasonable facsimile of your data, right? If you have data that are not shareable, very often in social sciences we deal with data we can't share with people. It's hard enough for us to get access to it to begin with. I spent this entire term trying to get 2 data sets for my CPSR. They still haven't come into me, so I can't imagine anyone else is going to be able to get those data to easily replicate my results. I could, however, fabricate a reasonable facsimile of those data that I could give to somebody to show all of my results will hold with similar data, right? Okay, shared code. Other people cannot reproduce your research if they don't have the code you use to generate your results, clean all your data, all that sort of thing. You have to share your code because that makes the decisions you make in the workflow of your study clear to other people so that they can judge them and maybe find them fail. Next, documentation. So if you give people the data and you give people the code, but your code is completely impenetrable and they have no idea what things are doing, it's going to be hard for them to reproduce it, or at the very least hard for them to judge whether what you did is correct. So the operation of the code should either be self-documenting. Code is somewhat self-documenting if you do RMD files and break up things relatively well. You can follow a flow of it, especially if you're using kind of like the dplyr type tidyverse stuff. Anybody who's reasonably competent with those things can probably follow the flow of things that are done. We'll see how you feel about that when I show my example here at the end, and my one next week. But sometimes they're relatively self-documenting. Or, if it's complex, you will have written descriptions to make its use clear. Writing documentation is something that isn't often done in the social sciences. When it's done, it's often not done well. But writing documentation is something absolutely required everywhere outside of academia. If you go and do some sort of research type project at a company, you go to Google, you go to Amazon, you go to Facebook, they have huge amounts of documentation built into all of the code. Tons of comments, explanation, definitions of input and output for every type of file, everything like that. If you don't write that documentation, you're going to get fired. Sometimes they have entire departments of people who write the documentation on these things. I have a friend who's a data scientist at a company recently, and his job is essentially to write the main code, but other people's job is to come and meet with him and write the documentation for it. Documentation is really important. We don't do it well enough usually in the social sciences, so you either want to make your code self-documenting, that is obvious, clear, described as you go, or actually write real written descriptions. Lastly, there is version control. Version control is something that's probably most likely out of these three things to be new to people in this room, and I'm going to have a section today on version control. Version control is a way of documenting the entire research process, not even just the code or modifications to the data, but every decision made along the entire way. And it's also something that prevents losing your work and makes it easier to share your work with other people, essentially by continually backing it up, archiving it, and allowing people to go through the history of everything you've ever done on a project. The idea of sharing every change you've ever made to every file in your project is scary to some people, but it's something that is, in my opinion, important. Okay. There's a lot of different levels of reproducibility to research. For academic papers, it used to be that the most common reproducibility was to tell people to read the article, right? You'd be like, well, everything is in the article, they'd say. Well, no, usually not, except maybe if it's a math paper, right? Two, next is shared data with some kind of documentation. This is essentially when you, back in the day, you'd often email an author and be like, okay, I read your paper, I was wondering if you could send me your data and an explanation of how you did the analysis. They might send you the data with a little bit of write-up being like, oh, this is what the buttons I pushed in SPSS to spit out the results that I got. This is a step up, but it's still not really something you'd call reproducible. The next would be to get the data and have them give you all their code. Maybe they give you a stata-do file and they're like, okay, this runs all the analysis, does all these things. Right? It doesn't have any, good documentation. It's probably messy. You probably have to modify things in it to make it work on your computer, but at least, theoretically, if you can get it to recognize things in your environment the same way they are in their environment, you might be able to get the same results as them. To get the paper produced, you'd probably have to copy and paste results out, put them in a paper, type things up, generate your own tables, that sort of thing. And that's only if it's in one do file. Very likely it's in 1,000 different do files producing tons of files. Some of them are filtering. They're not well named. Every single one of them is named something final, even though there's like 5 different versions of that, like final version, oh, final version 2, final version 3, that sort of thing. That's what at least all the projects I get assigned to look like before I get to them. The next is an interactive document. Well, interactive documents are what we've been producing in this entire term, right? All of our RMD files are interactive documents. This is a step above just sharing the data in the code because it's something where the document doesn't even work unless you can run the thing, and everything is usually done in one place. It just shows it as you go. You might have to modify some stuff at the top if it's not made portable. I'm going to talk about portability in a minute. But by and large, everything's in one place. Maybe it even does fill in the results in the paper like I talk about doing, but I haven't made you guys do too much in this class. And your analyses are everything's done in one spot. The document sort of runs itself, and it kind of documents itself, especially if you're writing up some stuff as you go. Above this would be something like a research compendium, which we'll talk about a little bit today. A research compendium is a fully portable project. It would contain, say, a zip file that has all of your data, all of the code used to run it, all of the like subfolders that contain, you know, derived data, all the scripts that run everything, all the functions used to call on it, and maybe a single .rmd file that compiles everything together into one paper. This is a step above an interactive document, because rather than just being, say, an individual RMD, it might be dozens or even hundreds of files, but it is the entire project. And in a research compendium, they're designed in such a way that if somebody downloads that compendium, opens it on their computer, as long as they have the R packages installed that it says are required to run it, it will immediately run and generate the paper on your computer. This is how I package my articles usually, is what is called a research compendium. There is a step above this, which I do not do myself, but I have friends who do, which is called a Docker compendium or a Docker file. A Docker file goes beyond the research compendium, which is a self-contained project, to being a self-contained computational ecosystem. A Docker file is something you download. It has the research compendium in it. It also has a very small, fully functional Linux operating system and a complete like R and Python environment in it. So you could go load it on any other computer anywhere, and it will actually contain all of the packages, the R installation, the exact version of everything that was used to generate that article when that article was written. Because software changes over time. The Docker encapsulates it all as sort of a time capsule. If you go to that Docker file 15 years after it was run, it doesn't matter. It will still run because it's a fully encapsulated little computer ecosystem. Some people I know package their stuff like this. It's actually, sounds hard to do. It's really not. I just don't do it because I'm lazy, honestly. Okay, so interactive documents. We spent most of this class using interactive documents. So I don't have to dwell on it. Our Markdown docs are a good example of a type of interactive document. They are maybe not the most common type of interactive document. I'd say Python notebooks are probably the most common interactive document right now, Jupyter notebooks. But anyway, interactive documents of any kind just combine code and text into some self-contained document, right? You can load and process your data, run your models, generate your tables and plots, inline text, automatically filled in, all that jazz. They let the reader examine all your computational methods within the document, and that can make them self-documenting. It might be borderline if you're doing stuff really complex, or that there's so much code in there that, you know, people can't possibly parse it all. But for the most part, people should be able to follow the flow of the document. By rerunning the code, they can then reproduce your results on demand. If you can get an RMD file from somebody and run it, and it immediately produces different results than what they showed somewhere, you know something is wrong, right? This is nice. It just reproduces it or doesn't reproduce it, and you can yell at them if it doesn't reproduce it. Common platforms, like I said, are in our Markdown. There's a link here if you want an example of one of mine that's actually kind of going into a paper working on now. And then the Jupyter notebooks, if you've ever seen those or you work in Python. Pretty similar. They can both produce like final PDF nice documents. Research compendiums are portable, reproducible distributions of an article or a project. They feature an interactive document as their foundation. So everything will be centered around some interactive document, some RMD or Jupyter notebook. They will have files organized in some recognizable structure. I like to organize mine to match the structure of an R package, and I distribute my articles as R packages so people can do install.packages and it will pull down my articles onto the computer, which is, I think, a cool way to do it. They have a clear separation of data, methods, and output. Data are always read-only, so you have some unmodified, never touched raw data file. No operations will ever be done to it. It just gets loaded into R, processed, and everything, but the original data are untouched, usually exactly as they arrive to me from, say, the NLSY or something like that. And then also they will have a well-documented or even preserved computational environment. In the articles that I produce, I usually have a colophon at the end that says every package that was loaded in the process of generating that RMD file, the date that it was generated, the date those packages were installed, all the links to those packages, citations for them, all that kind of thing. So if anybody wants to replicate it exactly the same computational environment I use, they can just get all those versions, make sure it runs exactly the same. RR Tools by UW's own Ben Marwick has a simplified workflow to accomplish this in R. So I use RR Tools about half the time to do this sort of thing. It basically just gives you a framework for generating research compendia. It automatically creates the folders on your computer, creates a sort of a not exactly blank, but an RMD that's filled in appropriately to produce a journal article. So it has integrated reference management, it has a nice format, it can produce HTML output or PDF output, that sort of thing. It's really quite nice. This links to a research compendium of mine. If you're interested, I'll actually just click it so you can see what it looks like. So research compendiums usually get packaged as a GitHub repository. This class is a GitHub repository too. The README will have something like the name of the R package that is associated with this compendium. So this particular article I'm working on, which is a dynamic intrafamily model of child behavior problems of birth timing with my advisor, is called birth timing. So if somebody could download and install this package using the dev tools install GitHub and grab this, it automatically produces this RMD, tells people how to cite it, how to download and install the package, and gives general information on it. And then I have links. So for instance, this is the paper itself, the paper that's automatically sort of generated for the RMD file that our tools put together for me. Looks kind of like a normal HTML version of a paper. It has embedded diagrams. The references are actually managed within the compendium itself, so this entire list has been formatted properly and output by the package. If I don't want this in ASA format, I literally just change from ASA, say, to APA format. It will reformat all of my reference section, and all of my in-text citations will change to the appropriate format, stuff like that. If you manually type your reference sections, you will immediately realize how much time it can save to package things like this, and it pulls these references straight out of Zotero, so I don't even have to tell it what things I need to begin with. And then you'll see at the end of this is that colophon I talked about. This report was generated the last time I compiled the paper. It tells you the version of R I was on, my system, the date, every package that was loaded at the time of compiling this paper. It's reproducible. The environment is documented. It's not self-contained, but it's fully documented. Okay. So, Bookdown. Bookdown is a package in R and a way of approaching generating reproducible documents. Bookdown, which is, I'll note, integrated into RR tools, and that article there is produced using Bookdown, generates documents in the proper formats for articles, theses, books, dissertations, but using Markdown instead of, say, using LaTeX or a LaTeX template to generate that output. It's nice because it's a lot more accessible than learning how to write LaTeX, but it does the same typesetting as LaTeX and the same reference management that you can get in like a nice LaTeX distribution. You can integrate your citations and automate your reference page generation with BibTeX files, so Zotero will output BibTeX files. They'll automatically be managed by Bookdown, put in appropriately. You can do in-text citations, all that stuff. It takes care of all of it for you. So Bookdown does HTML output the same way R&D files do. It also renders to PDFs through LaTeX for publication-ready documents. So you can have things come out not just as a PDF, but in the exact format using LaTeX templates that journals might make you send them an article in, or the University of Washington might make you produce your theses or your dissertations in. The HuskyDown package is another Ben Marwick creation that uses Bookdown to produce University of Washington theses and dissertations using the official University of Washington LaTeX templates. Without you ever having to write any LaTeX, you can just write a .rmd file, but it will render and pop out looking like a UW dissertation or thesis, so you don't have to do any of that formatting manually. This is really nice in how my dissertation is going to be formatted, and to a degree how my thesis was formatted. I had to modify it for my particular uses because I'm very anal about how things look. Now, pretty neat. Recommend that package a lot. It's very simple. Okay, anyway, off of that. Now we're going to talk about best practices. So this is going to be 20 or 30 minutes of me ranting about very small sounding things that I believe are very important. Okay, so the first thing, organizing your research. So organizing your research projects is something that I say you either do accidentally and always badly if you do it accidentally, or you do it purposefully with some upfront labor. Uniform organization that is making every single project you do exactly the same makes it a lot easier to switch between projects and also revisit your old projects. I like organizing things something like this. I recommend other people do something similar. You'll have some top-level project folder named whatever that project is. It will have a README file here. The README file can have anything in it. I like doing GitHub-style README files because my projects are also GitHub repositories, but you can do anything you want. Then I'll have a data folder, which will have derived data. This is the data produced by R or whatever programming language I'm using. All of it will be in there. There will be some raw data. This directory is entirely read-only. Nothing here can be modified. This is where I'd have my original, say, CSV files, but I could have shape files. I could have anything in there. But those are things that will never be modified by the project. I'll have some docs folder. That would have my main RMD file in it. It might have anything that goes directly into the RMD file, like my tables may be their own individual documents, my images might be their own individual documents, they'll be in there. Then I have a syntax or code folder, which has functions I generate for this project in a .r file, the models that I run in a .r, it'll have scripts that will also do the sort of cleaning and processing of the data. That will all be in here. Notice those files are not in my .rmd. I'm doing all that outbound, and it gets piped in and sent to my RMD later. This kind of organization is nice. There's a clear hierarchy to it. It's obvious where any given thing in a project goes. So if you're searching through your projects and you know exactly what it is you want, you know right where to find it. You don't have one folder clogged with 50 different files. God only knows what they are. The naming is all uniform. Everything is lowercase, has underscores here. It's obvious what everything is. The names are self-descriptive. Nothing here is ambiguous. If you have ambiguous files, like you open up a folder, you see anything you don't know immediately what it is, you should be renaming that file. Because if you come back to some research 2 or 3 years later, which sadly happens to us all the time because we get sidetracked on stuff. I have projects that I've abandoned for like 3 years. I come back to them, and if my stuff is not well organized, the first thing I'm going to do is I'm going to open up and be like, ah, shit, because I have no idea where I left off with that project. I don't know where anything is at, whatever. I sometimes can't even tell, oh, version 1, and then one of them will be named like version 5, the other one will be named final. God knows which one of those is actually the most recent one. Don't do that. When I stopped doing that, my life became a lot better. Okay. Another thing to do is to separate your workflow from your project. To summarize Jenny Bryan is works at our studio and at UBC up in Vancouver, and is one of the, probably, actually, as far as I know, the best teacher of R anywhere, like in the United States. Legendary. A lot of the course material that I have here is in some way indirectly based off of stuff. One should separate your workflow from your projects. Actually, I think the quote from her is that, for instance, if you set a working directory in your document, I will come to your house and burn your house down, or something like that. Got very upset about it. Workflow are things like the software you use to write your code. If you use RStudio, if you use Emacs or Vim, use something other than RStudio, that's part of your workflow. It is not part of your project. The location that you store your project in is part of your workflow and is not part of the project. The specific computer you use is part of your workflow, and code you ran earlier or typed into your console is part of your workflow. It is not part of your project. Your project should not rely specifically on any of these things. So what's your project? Your project would be the raw data you're using, the code that processes your raw data, maybe runs your models, that kind of thing, the packages you use to get your results, and the output files or documents for that project. Nothing over here should rely specifically on anything over here. So long as a person has their own one of any of these things, all of this should work for them. It doesn't matter what environment they're in. Most people use RStudio. Some people do not. Some people use Emacs with R does Emacs or whatever it's called. It should work perfectly fine for them, right? The big one that people usually mess up is the location you store a project is hard-coded into the project with something like set working directory. That means for anyone to run your code, every time you set a working directory, they need to overwrite that command with the appropriate directory in their computer. This is bad. That is making your workflow part of your project. It even means that if you copy that folder to another location on your computer, none of your stuff will run, right? It could be bad for you. Past you is usually current you's worst enemy and a terrible collaborator. Setting working directories and stuff makes future you not like you very much. Okay, so projects should not modify anything outside of the project at all, or need to be modified by someone else. That someone else is usually future you, but sometimes you'll be collaborating with other people. It shouldn't need to be modified by anyone to work. They should be completely independent of your workflow. Okay. So, for research to be reproducible, it has to be independent like this. It has to be separated from the workflow, which means it must be portable. Portable software is software that works independently of workflows such as fixed file locations. You probably don't even have to think about it, but most of the software on your computer is already portable to some degree. You can run it anywhere. Very often you'll have applications you can put anywhere on your computer. They will work perfectly fine everywhere. Sometimes you can put them on a USB stick and plug them into any computer. If they work perfectly fine, that is portable software. Nowadays, it's very common for software to be fully self-contained and portable like that. If you want people to be able to move it around, reproduce your stuff easily, it needs to operate independently of your workflow. Ideally, for it to be reproducible too, it needs to work on any platform, which is more than we can say for most applications. Somebody who runs it on a PC should also be able to run it on a Mac. Well, even if somebody has the exact same names for folders on the computer, if you move it from a Mac to a PC, they don't use the same hierarchy structure for files, so no matter what, it's not going to work, right? Okay, so these are things you should not do, basically ever. And it's okay, I'm guilty of doing these things and have been guilty of doing these things in the past, but these are no's. Do not set your working directory in scripts or .rmd files. Do not do this. I let people do it in this class, and sometimes I'll just at most shake a finger or something, but it upsets me. So please do not do that. Eventually it will upset you too. The next, do not use absolute paths. Absolute paths being like C drive, my project data, my data CSV. You're specifying the exact location on the computer. This is bad, because if anything moves, the whole thing breaks. There is one exception to this, however. If you have a fixed, completely immovable source on the computer, say you have a dedicated secure data drive on a secure data computer that cannot and will not ever be moved, might as well use an absolute path, because other people can't reproduce your research anyway, because it's something that's immovable, secure data. In reality, though, you still shouldn't do that, and you should use relative paths, because maybe you're going to give people a made-up data set to be able to reproduce your stuff, in which case that fixed path will break. The next, do not ever put install.packages in a script or in an RMD file. Install.packages is a command that should only ever be run in your console, because once you install a package, it is installed. If you put it in a script, it will break things. The computer will scream at people. I already have that installed. RMDs with installed packages in them usually won't run at all, because the RMD files do not like people doing that sort of thing. It's actually kind of a security problem to allow a reproducible research thing to install things on your computer. That's bad, so don't do that. The next, and this is one that in this class, I haven't told people about this command too much. Do not use rm list equals ls anywhere but in your console. Does everybody know what this is in here? Is there anybody who does not know what this does? Rm list equals ls clears everything from your global environment in R. It is a way of partially wiping R if you want to start kind of fresh. It doesn't remove everything from your computer. It doesn't remove packages that are currently loaded, stuff like that. Do not ever put this in a script or an RMD file. If somebody asks you for help on something and loads your script and it runs your script, it will wipe everything in their environment. If there's somebody working on their own project and they decide to load it up to help you, you just fucked up their day, right? You just like wiped it. If you're somebody like me who sometimes runs things that take 30 minutes to run or something like that, and I somehow miss this and do it, I'm gonna be really upset. Mostly at myself, but maybe a little bit also at whoever sent me that file. Don't do that. In fact, most of the time you shouldn't need to do this at all, for a reason I'm going to talk about in a second. These are things you should do. To set your directories, use RStudio projects or the here package, or base everything off the location of an RMD file. Wherever an RMD file is on your computer, it treats that as its working directory. Well, if you just put the data either in the same folder as the RMD or in a subfolder next to it, you can use relative paths to load files. So like, let's say I have an RMD file that's located in this My Project folder, and I want to access my data.csv. I could say read.csv./data my.data.csv. It's relative. This dot says the current directory, slash says data says looking data, and then get my data.csv. I can now take that project folder, copy and paste it anywhere on my computer, and everything will run just fine because it paths relative to that location. Relative paths good. Absolute paths bad. Burn them. Okay. Next, all required packages, load them using library. Make sure your packages are loaded using library. You do not want to load library like in your console. Load up a package, use it in your RMD, and then later go back and you're like, why doesn't my RMD knit? It's because you used some package you loaded locally in your console, but you did not load it in your RMD, so it can't knit because it doesn't load it. Because when you knit your RMD, it runs in a different instance of R than your console. The next one, so instead of using rm list equals ls at the beginning of every one of your scripts and RMDs, use clearing your workspace. Clear your workspace every time you close RStudio. I have it set up so that if I close RStudio, I open it back up, it wipes everything. It wipes everything that was loaded, my packages are unloaded, everything like that. I start fresh every single time I open RStudio and every time I swap between projects. You could set it up that way by going Tools, Global Options. It'll say Save Workspace to like our data file. Set it to Never. Burn it. When you close it, you want it dead. Do that. This will prevent you from ever running into problems where you're like, oh, something works when I'm typing on my computer, but I knit and it doesn't run. Well, because you had something loaded that was not in your RMD. You don't want that to happen. Burn it when you close it. Okay. If you do all of these things and you do none of these things, your work will probably be portable. Other people will probably be able to load it and reproduce your work. This is good. Okay. So, very often, in fact, in my experience, basically always, I don't want to include all the code for a project in a single .rmd file. Most of the time, my projects are sprawling and massive. As you've seen in this class, I write relatively compact code. It still ends up being way more than I want to put in a .rmd file. So, and there's reasons for that. One, often it just takes too long to knit. If I'm running these big hierarchical models that take 30 minutes, an hour, 8 hours to run, I don't want them in RMD because then somebody's like, oh, Reproducible Research knit. You just lock up their computer for 8 hours. Shouldn't do that, well, unless you don't like that person, they don't know how to close it, and then in that case, that's kind of funny. But, yeah, other thing is that the file is so long it's difficult to read. You know, if I've got 400 or 500 lines of code in an RMD, that is way too much. You're mixing too much too much code with all of the text, it just is a jumbled mess. You don't want to do that. There's two ways you can deal with this. One way is to use separate R scripts or RMD files, which run things and then save their results in like the derived data folder in that project, and then it loads those results in the main RMD file. This is just dividing it up into pieces, which you can run separately. This is really good for loading and cleaning big data. If you have some data loading and cleaning script that takes, 20 minutes to run, you don't want that to be run unless you need to change the data in some way. So instead, you would include that script in your project, give it to other people, but you would have already run it and included the data that is the output from that script. If people want to, they could open up and rerun it, but the data are already there. You don't just have to run it every single time. This is also good for running slow models. Like I said, sometimes I run these god-awful hierarchical models that take all day to run. I would rather run the model, save the output, include the script, but not make them run the script. Instead, they're like, okay, if you want to rerun the model, here's all the code you can do it. You better do it when you go to bed and then get it when you wake up in the morning. Another thing you can do is you can use the source function in R to call out to another R script and run it inside of the .rmd. So if you do source and you give it the file name and the location to a .r file, what this does is it goes, opens that R script silently. It doesn't look like anything to you. It runs all of the R code inside that file, and then produces all the output from that, captures it in your environment, and then continues running the things in the RMD. This is a way to call out to things. This is good for running like large files of code that aren't really slow. Maybe there's 500 or 600 lines of code, but it's really, really fast. I would call to it out to source, so I don't have to have that 500 lines of code in my RMD, but it's still explicitly referenced. This is great. It's also good for loading project-specific functions. So let's say you've written a bunch of functions for some particular project. You don't need to embed those functions in your RMD. Put them in some .r file, and then do source the name of that function's file. They will then all be loaded into the environment in the RMD without you putting those functions in the RMD file. This is external files. This is actually basically how R packages work. They just have source files that get loaded. They don't go into your global environment, though. They go into their own little environment. Yeah. Any questions about this stuff? This is actually pretty important. It's something I haven't made you guys do in the class because it's complex. But this is the way to organize things. You break it up into lots and lots of little files. That way you have tiny little files to deal with. I really, really like it when an R file stays under about 75 lines of code, and I will try and break things up until I have a dozen files that are all small like that with a really clear name. And then if I know if something breaks, I know exactly which file to open, and I can see all of it on screen at the same time. That's how I like it. Yeah.
I got a question. So I'm working with like a large data set. We had to make a bunch of stuff
Mm-hmm.
and then share it with a group, probably like most people.
Yeah.
Like, would you have two different RMD files then? If you like, how would you? Do you have this big data set that is all string variables? You need to like clean the dates
Mm-hmm.
and other stuff. And then you want to like filter it down to like just 5 variables instead of 5 million
Yeah.
variables. So like, would you just have 2 different ones? Like, you don't want to run it the whole time because it takes like an hour.
Yeah. Yeah, you could break it up. And I'm actually going to talk a little about that in 2 slides, I think, about how you can actually break it into what's called a pipeline. So in software development, professional software developers divide things up into what they usually call a pipeline, and it's kind of probably what you're getting at. I would use, if something takes a long time or it's big, you could just use multiple RMDs. That RMD file, instead of producing like tables, plots, output, could just produce an RData file or a CSV file, and then the next RMD file can call on that CSV and RData file. So you can just chain them together. That might be how I would do that, especially if I'm collaborating with other people. If I'm collaborating with other people, I usually like it if only one person is working on a single document at a time, be that an R script or an RMD. If you have 5 people on a team and you have 5 different tasks, there should be at least 5 different files, so everybody's working on a different one. You'll see that in pipelines in a second to make it a little bit clearer.
You'll just have like one RMD for the cleaning, and then it'll give an output, and then the next RMD will just revert to that output.
Yep.
Great. Okay.
Yeah, and if you wanted to put all of those into a single document, like present them as a single document, but write them as separate documents, Bookdown knits multiple RMDs together into a single document, which is a cool way to do it. So if, like for a dissertation, you could have like 3 chapters and an intro be like 4 different files, and write them out, but it looks like it pops out as a single PDF. A lot of different ways to do it, but yeah, breaking it up is usually the way to do it. Doing too much stuff in one file is bad. Okay, so I call this the way of many files. So I find it beneficial to break my projects into what looks to other people sometimes like a ridiculous number of files. I will have scripts, sometimes multiple scripts, with specialized functions to do different things. Every one of these files might load with source, that functions file. I'll have scripts that load and clean each set of variables. So I'll have a different .r file for each set of variables. I work with the National Longitudinal Survey of Youth, 1979. Every single set of variables, of which I have about 15 in that birth timing project I have loaded up there, every single one of them has a different R script that grabs the data, cleans it, and then one R file that stitches them all together, and then another R file to shape that, and then another R file to run my models, and then another R file to produce each table and that sort of thing. You know, it's 20, 30 script files in there. They're all small, compact, they all have their own task. Okay, yeah. Scripts to run each set of models and make tables and plots, and then one main RMD that might run some or all of these files. That birth timing project, it just runs all of them. It goes back, calls on every single one of them, runs them all, stitches it all together, and reproduces the document. But maybe if those took a really long time, I wouldn't want to run any of them at all, and I just want to call on the RData files that exist. You could do that too. Okay, splitting up projects like that carries a bunch of benefits. One thing is that once some portion of the project is done and it's in its own file, you never need to look at it again. It's totally out of your way. Instead of having a file that you have like the first 100 lines of that code or something you're just skipping over continually every time because it works, you've sent it out to another location. You don't have to think about it, out of sight, out of mind. If you do need to make changes, you don't need to search through some huge file. You're like, okay, in my data loading, I need to add some variables. You can go to that data loading script, which is purpose-built only to load the data, and add something to it. Another thing that's nice is if you're producing journal articles, you could take entire sections of the projects and add or remove them really quickly because you segmented everything. You're like, well, if I just don't call that file, it doesn't insert this entire chapter or section of it. This is great for making appendices too. One small tweak, I can change an entire section of the paper to an appendix, which I did with a paper I had recently, where one of my favorite sections of the paper had to be jettisoned out to an appendix. It took me no time to convert it because it was all generated as its own separate file. The big thing, though, about splitting things up into many, many files is it is the only way to build a proper pipeline for a project. So what's a pipeline? Pipelines are what professional researchers and teams design projects as, right? A pipeline usually looks something, oh, actually I have it on the next slide. Pipelines are a series of consecutive processing elements that is like scripts and functions in R. Something goes in one end and comes out the other. Each stage of a pipeline has some clearly defined input and output. So it specifies immediately, okay, this takes a CSV file of these data, it spits out a cleaned data frame like this. It does not modify its input. Everything on the left side of it is read-only. Its output is all on the right side of it, if you imagine it's flowing left to right. And it produces the exact same output every single time it is rerun. The reason for that is it has never modified its input. It will always produce the same thing if its input is always the same. This means in a pipeline, if you modify one stage of the pipeline, you only need to rerun that stage and its subsequent stages. Once you finish something that's further down at the beginning, as long as it's done, you'll never have to rerun it again because its output is there, unless you modify it. This is great for things that take a really long time to run. Let's say you do a lot of stuff with Twitter data. Maybe you've had it scraping for 6 months or 12 months, like somebody I know who just has it perpetually scraping. That's part of a pipeline. They never need to rerun any of that stuff. It's just there. It produces the data out, right? Another thing, different people can work on each stage at the same time because everything is divided up in different pieces. Because it has a specified input and output, you know the format of the input and the format of the output never changes, even though the content of that script might change. It's well defined, so people can constantly work on it, but it's always producing the same thing and always taking in the same thing. So people could have teams work on each segment. This is how something like, Amazon works to develop projects. They might change all the interior code on some part of their workflow, but it always takes the same input and always produces the same output, so it never matters to the other teams. It's compartmentalized. This also means all problems are isolated within a stage. If something is going wrong, it's always within one stage, and it's usually easy to recognize it. You recognize it because maybe one stage says, I'm getting the wrong input. Well, you know it has to be the stage immediately before it that's messing something up, because it took its input correctly, but its output is coming out wrong. You've identified exactly where the problem is, you fix it there. Okay. In my opinion, one of the really nice things about pipelines is because it's all directed like this, you can depict your entire project as a directed graph of dependencies. In software development, dependencies are everything needed to run something is a dependency. This is what a pipeline looks like in software development terms. Every stage, which is some sort of bunch of R functions, is an oval, and everything else is input or output for each one of these stages. So for instance, let's say we have a bunch of CSV files, a whole bunch. We have some script that is load data. It loads the CSVs. It outputs a full data set that combines all those CSV files together. This full data gets sent to my descriptive statistics. This runs it, produces a descriptive statistics table, which is going to go into my final paper. These data also go to a reshape data function, which then puts out data for my models. Say it's reshaped so that my models are ready to run it. Maybe I do structural equation modeling. I mean, not maybe, I do it all the time, which requires a weird format of data compared to most things. So it has its own dedicated reshaped function, but it's not the same data that I want for my descriptives. That model data goes to my models, and then this script will output tables in PDF and plots in PNGs. Then the model tables, the plots, the descriptives tables go into a paper.rmd, where none of the analysis has taken place, none of the data shaping. I've just loaded everything in there, and it spits out a final paper PDF. If any part of this project goes wrong, I know exactly where it went wrong. Because if something fails here or here, his output is wrong. If something fails here, there's a problem with my CSVs I have to address, so on and so forth. Everything is isolated to a single location, and I can show somebody in a diagram. It's like, well, if you want to locate some part of this whole process in this project, this is the entire map of it. This is where everything is. This is where all of the intricacy is occurring. This is a pipeline. Sometimes pipelines are enormous. You can have pipelines that allow hundreds of different things in them, but they're actually really easy to browse. You can just follow it down this directed graph, because everything goes from one side to the other. You notice there's never any bidirectional or circular pathways in something like this. It's a directed graph. You just follow it all the way through. You want to avoid circular paths because that adds a lot of complexity. It just goes left to right. Any questions about this idea? Or how this works? The way it works in R is really easy, because this is just, this is an R data file, so this is just would read CSV, do a bunch of stuff, and then at the end it would be save full data.rdata. It saves the file. Then this would have load full data.rdata. This would also have load full data.rdata. and then they would output. This would then save that R data, and then it would load it here. Just creating a file, opening a file. If you wanted to skip a step like creating this file, you could instead, in Models R, do source, reshape data, and it would run that entire thing and put it straight into the environment. I like to do intermediate files like this for speed. Make sense? It's just an approach to things. It is the correct approach, at least according to the industry, but this is how I think projects should be organized. Very often your projects are implicitly organized this way, but you've probably never thought of them as being diagrammed like this. Try sketching out a project you have that has multiple files sometimes. You may find it illuminating. Okay. Now I'm going to give a little bit of even more opinionated advice, because you're my captive audience. So, on formats. It is my opinion, my strong opinion, that you should avoid closed or commercial software and file formats except where absolutely necessary in the name of science. Use open source software and open source file formats. It is always better for science to use open source software because people should be able to explore your research without buying commercial software. If you are doing reproducible research but you're giving every person SAS files, they need to have a SAS license or access to a SAS license to use it, right? You don't also want your research to be inaccessible when software is updated. This is something that happens very often with commercial software and very rarely with open source software. The software gets updated in some way and they make it incompatible with all prior versions of it, or the new version files can't be opened by the old versions. Stata does this regularly, SPSS has done it, SAS has done it. Lack of backwards compatibility. This is terrible for science because it means somebody has to go and purchase some commercial product, which is often a pile of shit anyway, like a SPSS, to even reproduce your work, right? And they're often not just better in these ways, but just plain better. Open source software is usually updated a lot more quickly than most pieces of commercial software, especially updated in the ways that are important, like security. Open source software tends to be more secure because every person who works on that software or uses that software can open up and look at the code. And some people as a hobby like to try and break software and use that software to like invade systems and things as a hobby. Patches come out really fast for open source software because so many people's eyes are on it. The only people's eyes on a commercial product like Stata are the Stata development team, right? They will overlook things, they won't add things. If nobody in that company knows how to do something, it will never be added to that software for the most part. Okay? Not so with open source software. If I want to add some functionality that doesn't exist in R, I will just add the functionality in R, put it in mine. If it's popular enough for other people, they will incorporate it. Download it as packages or make it part of a full R installation. Another thing is open source software is really, really rarely abandoned. Two of the most popular open source pieces of software in existence are Emacs and Vim, the text editors. Both of these date back to the 70s and everyone is still using them. That software doesn't get abandoned. It just gets updated, modified. They layer an interface onto it. God though, Emacs, I think Emacs is still, what is it under? Emacs is still a horrible programming language under the hood, but people still use it. Yeah, but it never gets abandoned. Open source software tends to be eternal. Sometimes it falls out of popularity, but there's still somebody out there using it. Fortran is an example of something that's essentially open source. There are still people in the climate science building who write everything in Fortran. It's fast, it's widely accepted, usable everywhere, it might be ancient, it's still there. No one will ever abandon it. Proprietary stuff and proprietary languages, they get abandoned. They die, they're gone. Okay. The ideal for formats, in my opinion, is to try and always use software that reads and writes raw text. Raw text has never really changed in its format. I can open a raw text file produced in the 60s on magnetic tape on my computer without doing any format modifications. It's basically eternal. ASCII has stayed the same. Sometimes the encoding has changed a little bit. Now there's like UTF-8 plain text. That stuff will be readable basically forever. Binary files, no. Word documents and things like that, other people cannot open those things. You ever try and open a Word document in a raw text editor? It's garbage. It's unreadable. There's no recoverable text inside. It's a binary file format. Avoid that. Okay, so text. Writing and formatting documents are two different jobs. It used to be, back before the world of internet slave labor, that writing and editing were two different jobs. There were writers. Writers would write things, they would give them to an editor, the editor would do it, and then the editor would either typeset it themselves or send it to a typesetter to do the typesetting. Nowadays, people are generally expected to write, edit, and typeset all themselves as if those are the same job, right? They are not the same job. You should write first and format later. You might not have been thinking about it, but when we're writing Markdown in our RMDs, we are writing first and letting it format for us. You notice that you just write, you break things up, it naturally divides things up and produces things. Maybe there's very minor formatting, like you say hashtag for a header. You're not specifying the font size of the header, the color, any of that. Instead, you give it a style sheet or a style if you want, and it typesets the entire document for you. It's separating those things. Word processors like Microsoft Word try to do the writing and the formatting at the same time and usually make both of them worse in some way. They waste your time. They waste your time by leading you to do formatting instead of writing. Have you ever found yourself procrastinating by changing fonts or bolds or the organization of a document? Maybe you're like, oh, I want that to be 18 point instead of 16 point for looks. You're wasting your time, and Microsoft Word has lured you into doing this. If you write in raw text, there are no fonts, there is no italics, there is no bold. You can't mess with your formatting because you have text. 1 second. I have to keep my rant going. Okay, they waste your time. There is nothing built into Word that cannot be found in a raw text editor. Nothing of value, anyway. Being able to do bold and italic and all that kind of stuff, change your fonts and stuff, is useless. It is a waste of your time because all of those things could be specified in the header of your document to say, format my entire document with this particular style, and it will just do the whole thing for you. It's the way LaTeX was invented in the 70s to do this. Well, tech was invented in the 70s, LaTeX in the 1980s. Yeah, because writing and formatting are separate jobs, and they should be done by separate pieces of software and separate programming languages. Okay. So, to that end, you should find a good modular text editor and learn how to use it. I like Atom. Atom is a really nice text editor. It's made by GitHub. It's super expandable. It has things like you can add to it, like it can process my code, it can lint it to look like RStudio, my syntax checking, but it also does syntax checking with my spelling and my grammar. In fact, it's more aggressive than Word could ever be because it does things like scream at me when I use words that aren't strong words. Like, it doesn't let me use modifiers that are weak modifiers. It doesn't let me waste words. Things like that. I've got it set up super aggressive. It can also parse other languages simultaneously, and it will let me layer code in the middle of it and recognize what is code and what is written language. It's pretty great. It also has a built-in terminal, so I can do like command line stuff like that. It has project management features. It links into Python. It links into R. Blah, blah, blah. It's modular. It can do everything. Sublime is something similar. I find Sublime a little harder to use than Atom, but a lot of people like it a lot. I also noticed did not provide links on these. Emacs and Vim are also modular text editors that are incredibly powerful. They're also arcane and angry, so very difficult to use. Emacs is the kind of thing that if you want to run a command in Emacs, you'll hold like Control-Alt-Shift-CD and it will do something. God only knows what it will do. Maybe that will open up email because Emacs is basically a self-contained operating system. Very powerful. Vim is also super powerful. If you were used to Emacs or Vim, RStudio actually has a Vim mode that works as a Vim text editor. Emacs and Vim are about the two longest running pieces of still used software in existence. Programmers very often work in Emacs or Vim, and usually Emacs users and Vim users hate each other, and it's like this holy war that's existed for 30 or 40 years. I don't put links there because I don't think anyone should use either of them at this point. I wish they would just die so I can stop hearing about it. Atom is really nice. Okay. Oh, another nice thing. Atom is written entirely, like all of its add-ons, all that kind of stuff, it's all in a mix of Python and HTML. So if you want to modify Python in some way, you can basically just modify it with writing HTML and a little bit of Python code if you're good at that. So you can just write all your own add-ons to it. That's super cool. Anyway. Okay. Next topic. Version control. So, version control is something like pipelines that emerged from software development. In this case, collaborative software development. The idea behind version control is that every change, every minuscule change in a piece of software should be documented, saved automatically, and importantly, revertible. That means every change that was ever made to something, you should be able to undo it no matter how long ago that change was made. Everything is always documented. And in fact, the documentation in version control is usually cryptographically secure, meaning it is actually impossible to delete the existence of a change that was made ever in it. Once a change has been made and subsequent changes have been made, there's always a record that change was made permanently. You can't, like, excise it from that record. Okay. Version control means every decision you ever make in a research project, for instance, is documented automatically. And when I say every decision, I mean everything. Every little bit of, like, exploratory analysis you ever did, every poking, every different set of variables you used could potentially be permanently saved as a record. This is the ultimate level of reproducible research, because it's not just documenting, like, how the final project works, it's documenting everything you ever did in the project to come up with the final solution. This is documenting the process of sciencing, right? Okay. Version control can protect your work from destructive changes. So sometimes you'll make a mistake, like delete something you want later. It's no longer gone forever if you have version control, because nothing is ever gone forever. It can simplify collaboration because it enables people to merge changes, even to the same document. One person works on one part of a document, another person works on the other one. If they both upload their versions, it will reconcile the differences and stitch the documents together. It's great for collaboration. It documents all design decisions. Like I said, everything you ever did could be documented in your version control. Everything I've ever done in this class is visible on the class website. If I go view the repository for this class, you will see I have 402 commits to this class. That means I have updated things in this class 402 times since I started teaching this class. You could see what every update and slide change, code change, homework change, lecture change I have ever done in the history of this class is. You could click up and see exactly what they are. For instance, these are the slides for today where I fixed typos and things. Instead of saying the location you store your files, I say the location you store a project, and I added bullet points. Everything I've ever done in this class is fully documented like that. Imagine your research being fully documented like this. And I do this for everything I do. Yep, this is version control. Other people can also make suggestions. They can take issues with things in here. They can see everything that's ever done, view every file, right? Okay, so that's transparent. My entire class is transparent. You can download it as a zip file. Hell, you could download every change, everything I've ever done in this class, right? Okay, so Git and GitHub. Git is the dominant platform for version control, what's most commonly used out there. Subversion is a little less common. Git was actually written by Linus Torvalds, who wrote Linux, or did the original versions of Linux. It's free, it's open source, it's pretty reliable, and pretty much everyone everywhere uses it. GitHub is a free, now Microsoft-owned platform for hosting Git repositories. A Git repository is just a project. Repositories are some folder on your computer where all the changes made in that folder are tracked by Git for you. If you make some changes, once you're satisfied with some changes, you commit them, and then you push them to your remote repository. This just means saying, okay, I've completed enough stuff that I want to save what I've changed. I hit commit. Then, if I want to send them to a remote repository, that is, archive them, you do push. I commit and I push multiple times per day on every project that I work on, because every time I push, a new version is saved somewhere else. I have 4 computers where all of my files on every computer are synchronized between all 4 of them. If somebody stole my laptop, stole my tablet, and my house burned down, destroying the other 2 computers, every file that I have on my computers is backed up on the cloud somewhere, and all of my academic work is also backed up on my GitHub. If I then got a new computer down, I could press one button, restore all of my projects from Git. It's pretty nice. And it would still restore the entire history of everything I've ever done on those projects. You lose nothing this way. Next, if other people want to copy your project, they can basically one command line command or one button press on the website pull down your repository. They can just download onto your computer, and they have every file in that repository, and they have the full history of every file in that repository. It just copies everything. They can then, on their computer, make changes to all those files, and if they feel like it, they could then say commit and push to you. You don't automatically have to accept changes people make. You'd see it. You could accept them if you want. But it just means everybody can collaborate, but everyone's always working on a local version of the file. They're not simultaneously editing like the same Google document or something. People can be developing two completely parallel lines of a project at the same time, and they never need to merge them if they don't want to. Sometimes people do this, they fork projects off. I have people who download my projects, fork them, use them for their own stuff. They never want to merge the stuff back in, they're just doing it for their own uses. It's completely separate, but if they wanted to, they could suggest, hey, I've made all these changes to it, would you be interested in including this code in your repository? I might be like, that looks great, and they'll send it in. This is how R packages actually work. Most people who develop R packages, everyone is doing it on some central GitHub, and people will find errors, they'll suggest fixes to them. They will push those fixes to the repository, somebody will accept it, they merge it in, and then the error's been fixed. The Linux operating system, everything's based on Git repositories for the central repository for Linux, and that's how people add new things to the Linux operating system and fix bugs in it. They just make push suggestions. I think the Linux operating system, last I checked, was getting like 1,000 commits or something per minute or something like that. Git handles it effortlessly. Okay. Constantly committing and pulling changes automatically generates a running history documenting the evolution of your entire project. This is great. You commit, you push, commit, push, multiple times per day. Every one of those commits is documented. Every change in each individual commit has its own record. Git is already integrated into RStudio under the Tools menu. It requires a little bit of setup and integration of a Git client on your computer. Not if you're on Linux, but actually Macs probably have built-in Git too. Windows requires a little bit of finickiness. There's also a desktop application if you don't want to mess with command line stuff. I actually use the desktop application because Windows is a pile of shit and it works really well. Yeah, it's there. I recommend using it. I recommend having every one of your projects done that. GitHub, if you are in education, including if you're a graduate student, you can have private repositories if you don't want other people to be able to see your work. So if you're worried about people scooping your research or something, you could still save it on GitHub but make it private. I do that with sensitive stuff. Okay. Another nice thing about doing this, GitHub serves as a curriculum vitae. So beyond archiving your projects and allowing other people to download them, GitHub is a CV for programmers. It allows other people to view projects you're working on, which will allow you to display your competence in programming and research. People can see that you know how to write code, you know how to write good things while they're in progress. You can actually attach your GitHub repository on your CV, which I do. I have my main GitHub link on there. If somebody who is in a, let's say I'm applying to an e-science type department, those people are definitely clicking on my GitHub to see what I can do. They can see all the code that I write. I will write better code knowing sometimes people are going to go peer and look at it, and that will advertise to them that this person is technically competent. If you're planning on working in the private sector, you really want an active GitHub profile. It will give you a leg up on anyone who does not have one. If you're applying to some technical field, everyone will have one. It's a good idea to have one. Showcase what you can do. People will look at them. People who do recruiting absolutely look at these and absolutely judge you based on the content of it. And it's far better to have one where you're not great in your code than to have none, because it's evidence. Next, if you're aiming for academia, a GitHub account signals technical competence and an interest in research transparency if you do your articles up there. It's showing that through the procedure of I'm willing to share my entire thing. If you're applying to some department that actually has technically competent people in it, especially like an e-science type thing or people linked to it, they're going to go straight to that and be like, okay, this is somebody along that will mesh in well with us because we use these tools and we have an expectations about reproducible research and sharing and things like that. I highly recommend having a GitHub that's active. Another nice thing, GitHub also does website hosting stuff, so you can literally host your CV in your main website there. I do all that stuff on my GitHub. Okay. So, that's the end of best practices, reproducible research, all that stuff. I'll be changing gears here. Do we have any questions about everything I've just ranted about for the last hour and a half? Yeah.
In GitHub, you use if you're dealing with secure data sets.
So, you probably, most secure data agreements are going to require you not upload them anywhere. So the answer is generally no, but that's nothing to do with GitHub. That's going to be entirely with what the agreement says. If the agreement says you can store it somewhere that is cryptographically secure in some way, GitHub has information on their security practices and storage, but it probably, if you're getting data from something like ICPSR, Now, ICPSR won't like it because they're going to want it on a restricted access computer or drive. It depends. Some places they'll be okay with it on a private repo. Normally what I would do is I would put all the code up there, but add to my... So there's a thing in GitHub repository, in Git repositories, called an ignore file. The ignore file, you just tell it what files in the repository not to upload when you mirror the repository. My project that I recently got that paper for I couldn't upload my police data, so I just have it ignore the police data. It still uploads all the code and everything, but the data can't be uploaded. Instead, I could upload a pseudo file, like it's not real data, but it's an example data people could replicate my work with. I upload that instead, and I'll just say that as a note.
It seems a little dangerous to me because it's like healthcare data. Like if you made one typo, then you would just have like 1 million HIPAA
Yeah.
violations.
Oh, well, you could even make it so that those data aren't even in the repository folder at all, so it would be impossible to get it. And then you could still relative path. You just relative path, like, out, and then you have, like, a companion folder next to it with a similar name, and you just, whenever you move both those together. Or the repository itself could be a subfolder in the overall project. I actually do that a lot, where my project has one big folder, but what's mirrored to GitHub is actually only a subfolder of that, because my project folders also contain like all the notes, my literature review, all that kind of stuff, which nobody wants to see that shit, so I keep it separate. Yeah. But yeah, a lot of people do stuff with super, super secure data, and still have GitHub repos. They're just not sharing the data. You just want to share the method, right? And then somebody else can jump through the hoops to get access to those data and then reproduce it. That's a limitation of, not the software and stuff, but just getting access to data. Common problem for me. Any other questions about this stuff?
So once you register the GitHub, how big the size of the space you can?
They don't limit you for the most part. I have one GitHub repository that's got 5 or 6 gigs of stuff on it. The main thing is you can't have a single file be over 100 megabytes, or they get a little upset with you, like it'll prevent uploading. But you can break them up in multiple files. So that's another thing. If you have a really big data file, just don't upload it. Put it in your ignore file. Upload the code, but not that file. Maybe include an extract and upload the extract as an example. Yeah, but I don't usually have big files on my GitHub because you don't want to have somebody be like, download and to reproduce your work, and they just downloaded a 10 gig file. It's kind of annoying. Yeah, but no main size limitations. I think they start to kind of get on your case when you get up into the like 10 gigabyte range. Storage costs nothing, and so they don't care that much. Yeah, they'll send you an email and be like, "Quit it" if you upset them. Yeah. Not that that's happened to me. Any other questions? Yeah, happy to talk about this stuff too, and help people get set up with those approaches. I think it's really important that we structure our research to be reproducible for science. And also, it tends to be better for us, because if you know other people can reproduce your work, you're gonna make it not garbage, right? And I find it is a nice motivator, because it feels like somebody's always peering over my shoulder. Yeah, it's great. Okay, so this is sort of a tangent, but I want to give an example of real-world, what I call real-world data management. That is encountering a problem that is really annoying and trying to come up with a solution to it. The solution I come up with is definitely not the best possible solution, but it is a solution, and it works. And you might encounter a problem vaguely like this. It's an idea. So, this, I'm using a small extract from the Denver Youth Survey, which is a 10-wave panel data set with 1,526 respondents aged 7 to 26. This is a data set I manage here on campus up in a little locked dungeon on the next floor up. Okay, a little bit of setup for this. I just do library tidyverse. Then I do this function, which most of you have probably seen in this class by then. I create my own operator here called %NotIn. We've seen the %in operator, right? Everybody remembers %in. It's for checking whether the thing on the left side of the operator is contained in any of the elements on the right side. %in is the opposite of this. %NotIn will return a true for every element on its left side that is not an element of the object on its right side. Okay? This is an inversion of %in. You'll notice I use the negate command to do this instead of just putting an exclamation point in front of it. It is equivalent to write exclamation point x %in y and to do %NotIn like this. These are equivalent because this inverts whatever's inside there. I find it easier to write this than to write that, so I write my own operator for it. You're going to see it a couple times in here, but just know it's there. Any questions about that? It's a handy operator. I recommend using it. I don't know why it's not built in. Okay. This is an example of the data set I'm using for this. So these data are actually, it's a small enough extract that it's available. You can download on the website if you're interested. This is a tiny sample. It has some columns, sequence ID, birth year, marriage end, marriage age, divorce age, censored age. It has a lot of NAs in it. Sequence ID are people. So this is person 1, person 2, or person 10, person 18, person 280, 417. Their first marriage, their second marriage, their third marriage, first, second, third, so on. So for instance, this person was born in 1974. They got married at age 23. They have no second or third marriages. They were never divorced, and they were observed until age 24. Censored age is the last age at which they are observed in the survey. This is a common sort of format you might get panel data in. That's really hard to use for any kind of analyses because it's got a weird format. These are a long type of format. Each individual has multiple observations. The observations are over time. However, the time is in age rather than years, and our observations are person marriages, which is a weird unit of observation. Variables again, unique identifier for people, a birth year, the number, marriage. Most people were never married at all or married once, but some people were married 3 times. Actually, in this data set, 5, 6, 7 marriages. It's a disadvantaged sample. People get rapid marriages. There's an age they were married for that marriage, an age for the divorce at that marriage, and some age they were last observed in. The goal, that what I needed to be able to do the type of analysis I want to do, which is a type of sequence analysis, it's a approach to genomic data, but I was using it for life sequences, is to get I need a wide data frame. I need a data frame where each row is a person. So a person only has 1 row instead of 3. Each column corresponds to an age from 10 to 26, and the values in those columns are 1 if they are married, 2 or 0 if they are not married, and NA if we have no idea whether they were married or not. So how do I convert something that looks like this, marriage 1, 2, 3, with age values in these over here, to something that looks like a big matrix of married and not married binary values? Well, the answer is it's kind of complicated, because this is not a normal structure of a data frame like in a dplyr sense we might do. It's really weird. So to do it, I do some advanced data manipulation. Okay, the first thing I do though, and this is the first thing I do anytime I encounter some weird problem I've never seen before, is I will write out what is sometimes an absurd amount of text. I like to write out these really long comments that just describe how I picture the particular problem and then brainstorm some strategies for it. So anytime I have a complex problem, I don't just jump into writing code. Instead, I write a whole bunch of notes to myself, being like, okay, this is what I think I have for data, this is what my problem is, this is what my end product should look like. Maybe here's one theoretical approach I think would work. Right? If you're interested, there's a link here to the unedited script. It's just the actual script that was in operation like last year that I was using for this. It's messy, it's long, it's inefficient, but it's real in-use code. This is the actual way these marriage dates are processed for this data set that is in use by multiple people on campus. You can't run the code because it requires the full data, but yeah. So I write out these big comments. And the idea I came up with is, well, what if I do a bunch of different loops over lists and convert it from lists into matrices? That's what I'll end up doing. So, the strategy I came up with is not necessarily the best way. In fact, I can guarantee it could probably be done in much less code, but this is the way I thought of at the time, was first, I want to get the ages in which individuals are known to be married. Just get those years of their life that I know they were married at some point in it. Which means if somebody's married once and never divorced, this is all their ages from when they got married to when we can no longer observe them. Maybe they got divorced after we can no longer observe them, so we're not sure. But we know it's at least the entire time they were observed since they got married. If they never got divorced, they were married. If they were divorced, the ages they're married are from marriage age to their age of divorce. If there's multiple marriages, it's just repetition of these two things. Right? Next, get the ages in which individuals were known to be not married. If someone was never married, they were just not married up until that censored age. If they were married and divorced, they were not married until their marriage age, and they were not married after divorce age until another marriage occurs. Everything that does not fall into one of these categories is an unknown or missing age. It's something we don't know about, so those are going to be NAs. So the goal is to make a matrix of individuals, individuals are rows, of given ages, which are the columns, and populate each one of those cells using 1, 2, and 3. 1 generates the 1s, 2 generates the 0s, 3 generates the NAs. Right? Makes sense? Okay. And see, this entire thought process occurs before I write any code at all. Because it's a hard problem, so I want to have a really good idea what I'm doing. Next, I start writing lots of garbage code, which I'm going to walk through. Okay. So the first thing I want to do is I want to get a list where each element of the list is a vector of the married ages for each marriage, right? So that means a person will have 3 elements of this list. Person 1 will have 1, 2, 3. This is going to be the ages they were married for their first marriage, the ages they were married for their second marriage, and the ages they were married for their third marriage. So if I have 6 people, there's going to be 18 entries, 3 for each person, each one being a vector of the ages that they were married in. Okay? To do that, the married years is equal to a vector list n row mare ages. If you remember, mare ages already has 3 rows for each person. Well, I want 3 list elements for each person, so I can just take the number of rows in it and make that many elements. It will be the right size. Then, remember what I said earlier about writing loops, how you shouldn't use loops? I used a loop for this because it was the only way I could think to solve this problem. Often that'll be the case. Exhaust all their possibilities, and then you end up with a loop. Because when in doubt, a loop can definitely do it. This is also a small data set. 1,500 people is nothing. This loop runs instantly. So, what I do here is I assign some names to these married years, which is just going to be the person's sequence ID dash their marriage number. Person 500 is going to get 500-1, -2, and -3 for their 3 different marriages. Then I run a loop over every element of mare ages or every row of mare ages. So I'm running this loop one time for each observation of a person, that is for each person marriage. This loop runs once. I say, if marriage age is NA, there was no marriage, so assign an NA if there is no marriage. Else, if this person was married, that is their marriage age is not NA, we're going to do something. What we're going to do is, actually in this case, we're going to check, were they divorced? So is this person someone who was married but never divorced? This was the first condition I had back in my list on this one. If somebody was married once and never divorced, then they were married from all ages from marriage age to censored age. So I say, if you were married and never divorced, then your marriage age here, if marriage age is less than or equal to censored age, assign all of the ages from marriage age to censored age to that vector. This is me literally taking the text I wrote on the previous slide and making it into code. This is just say the person was married at age 23 and divorced at age 25. This is going to be 23:25. So it's going to be the numbers 23, 24, 25 assigned to it. So if a person was married for those 3 years, their vector is just those 3 ages, right? Then I had to have a separate condition. If somebody was married for only 1 year, just assign that 1 year because the colon operator didn't like in this particular case going from 24 to 24 would produce 24 and then 24, not just the number 24. Programming. Then, okay. Else, if somebody is married and they were divorced, then instead of going to censored age, it goes from the age they were married to the divorce age. And then repeat this for each marriage for each person. Right? And then, if none of the above conditions apply, produce an error. But the thing is, there's only 3 possibilities that should happen. Somebody was never married, they were married and never divorced, or they were married and they were divorced. Those are mutually, like, that's everything. It should encompass everything. So this error should kick out if we have some problem in the code. Built-in error checking is really important in loops. Okay. This is what you get out. Remember? The first person was never married. So, NA, NA, NA. They were never married. The second person was married at age 23, and then we didn't observe them after age 24, so they have 23 and 24. NA and NA for their second and third marriage because they had no second and no third marriage. It works. It gets exactly what I want. That is a lot of code to get very little information here. But if you have 1,526 people, you sure as hell don't want to do it by hand. Next, what I want to do is I want to combine each person's 3 vectors into a single vector of married ages. So somebody who's, say, in their first marriage, they could be, like, they'd have 23 and 24. Their second marriage could be 24 and 25. I want to combine these together, but I don't want it to be 23, 24, 24, 25. I want to get rid of duplicates, but I want to combine them all into a single vector, right? I do this way. I make a new list, which is equal to the number of unique people. So there's going to be 1 row per person, but per unique person. So if there's 6 people, there's 6 rows instead of 18 like there were before. Their name's just going to be the sequence ID underscore the person's actual ID number. Then I do a simple loop again. I do 1 to length of age year yes list, that is the age years people were actually married. The values are going to be equal to, and this is kind of a mess, so married years before, right, is this list that has element 1, 2, and 3 for the first person. For the second person, it's element 4, 5, and 6, right? So I had to do some shenanigans to get the correct stuff out of here. I say, so imagine that let's say we're on the first person, so I is replaced with 1. This says the values they were married are equal to I times 1, or I times 3, so that's the number 3, minus 2. 3 minus 2 is 1. This is the first element of married years. This is minus 1, so it's the second element of married years, and this is the third element of married years. Combine them all together with C. So this says take this, and concatenate them together into a single vector. Then, when this I increments to 2, this is going to be 6 minus 2, 6 minus 1, and 6. Well, that's element 4, 5, and 6. So element, I went the wrong direction. This is element 4, 5, and 6. So this is a way for me to convert something that is 3 elements per person to something that's 1 element per person. Right? Does that make sense what that's doing? It's okay if it's a little weird. Then I say, if it's always NA, so if you put together all the married years and it's always NA, that's only possible if someone was never married. I just want to leave it NA. Otherwise, I take all unique non-NA values and put them together. So if somebody was married in age 23, divorced at 24, remarried at 24, divorced at 24, remarried at 24, and then divorced at 25, it will still be 23, 24, 25 because it gets rid of the duplicates. So what that does there. Then we get a list like this. Person 1, person 2, 10, 18, 280, 417. This person was married at 23 and 24. This person at 15, 16, 17, 18, 19. This person at 17 and 18. 18, 19, 20, 21, 22, 23, 24. This person, 18, 19, 20, 21, 22, 23, 24, 25, 26. There are divorces in here, but the people get immediately remarried, so there's no actual gaps. Now, okay. Well, now we have 1 element per person. This is getting closer to what we want. But we have to repeat it for unmarried ages, which I'm just going to breeze over. Basically, I'm doing the same kind of thing, except I make one assumption. I assume that nobody was married at age 10, or right? It's not a perfect assumption in a data set for a disadvantaged population. Marriages at age 10 occur in disadvantaged populations, but it's relatively rare. I just make an assumption nobody's married at age 10, and say 10 until a marriage occurs, they were unmarried, and then after divorce is to censored, so on and so forth, but it's the exact same strategy as the last slide. Now I get this. I have a vector of the numbers where people were unmarried. Right? As the gaps where they're unmarried. But this is unmarried for each marriage. This is here saying that, for instance, this person was unmarried for marriage 1 in these particular years, but it's a different list for unmarried for marriage 2. Because marriage 1, they were married at age 24, but in marriage 2, they were not married at age 24. Well, I have to reconcile all these lists, which takes a little bit of it, where I just combine all the unmarried ages into a single vector, but I make it so that if any particular value is missing, it's also removed from the other ones. So because 24 is here, I remove 24 from the other ones. It reconciles these lists down to look like this. These are the unmarried ages for person 1, 2, 10, 18, 284, 17. Okay? Now, I write some sort of giant function that will convert both of these lists together into a single matrix of 1s, 0s, and NAs. So, I write a function. The function will generate a matrix whose names are equal to, or whose columns are equal to ages 10 through 27. So I'll have columns age 10, age 11, age 12, so on to age 27. Doesn't necessarily do age 27. These ones only go to 26, but I did it anyway because there was a couple of age 27s in full data. There's 6 people, so I loop over the 6 people. And what this just does is it runs through all of these numbers. The earliest age in that list is age 10. So I subtract 9 from these numbers. And then, if they are in the unmarried list, I assign a 0 to that index of that row. So age 10 is the first element of that row. 10 minus 9 is 1. It would put a 0 there. To fill in the 1s, it goes to the married ages and it puts 1s in there. And populates the entire list left to right, row by row by row. If I look at what I get, we get something like this. Each row is a different sequence ID, a different person. Then I have age 10 through age actually 27. When they are unmarried, they have a 0. When they are married, they have a 1. And when they are censored, they have an NA. This is what I originally set out to do. It took a lot of steps to get there. It could have been less steps, because I could have written it more compact, but it would have been really hard to understand what was going on. It's hard enough to understand what was going on with me explaining it like that, and me reading the comments to this code. But because it was a really weird problem, I could not think of a dplyr solution to it. I might be able to now. I wrote this like a year and a half ago. Probably could figure out a dplyr solution, but it was really complex. I check the input, I check the output, or I check the input, I come up with a desired output, I write up a plan, then I try and execute it in code. Okay, so the idea here, this is a slide that's mostly a repeat of week 7 slide. Data wrangling can be really complicated. There's usually many valid ways of doing something, basically an infinite number of ways of solving any problem. The approach I take, which I recommend, is to look carefully at your starting data and figure out what you can actually get from them. There's no reason to start programming if you can never get the output you want from it, because the data just fundamentally don't contain that information. But if they do, figure out exactly what you have, diagram it, make sure you know the exact shape of these data. Then determine precisely what the end product should look like. You look at it and be like, okay, this is the format I want. 1 person per row, 1 age per column, whatever the hell you want to do. Get exactly that. Identify steps to go from 1 to 2. Make each one its own set of functions or function calls. If you look at what you've constructed and it is in some way confusing to you, break it into more steps. The examples I just did were the largest possible steps that I did not find confusing to myself. I could have done all that in a single loop. I did not do it in a single loop because it was confusing when I wrote it that way. So I broke it up into steps. Then complete each step separately in an order. This relates to the pipelines thing I was showing earlier. If every single one of your steps is like a step in your pipeline, known input, known output, your output looks like what you want, break it into steps. You may eventually want to go through 5 steps to get it. You could make them separate files if you want. But even if they're not separate files, imagine it's a pipeline within the script going from one end to the other end. That's actually what dplyr chains are. It's a chain of inputs and outputs. The input isn't changed by the thing on the right side of the pipe, right? It's just a pipeline. Okay. Don't continue until a step is producing exactly what you need for the next step. Verify it is exactly what you want. And then don't worry about combining steps for efficiency until every part of the entire pipeline works. There's no reason to make something efficient if it doesn't get what you want to begin with. And don't even worry about efficiency at all. If you can get something to run, you can make it fast later. But making something fast that doesn't work is pointless. Once you're finished, if you need to do it again, make it into functions or something like that. Or a package if it's something complex and you're going to do it a lot. Okay, so that's about it. You have an optional homework you don't have to do. If you feel like doing it, you don't have to peer review it or anything. I will grade all of them myself. It's on GGMap. I don't have any SF stuff in there because it's kind of complex. But yeah, if you want to, send it in next Tuesday. You get extra points for people who like points. I don't know. You won't need them. Everyone's passing last I checked. Yeah, that's about it. Thanks for coming and listening to me rant. Sweet.
Is this the last class?
No. We have one more.